All right. Our next speaker this morning is William Yang, who's joined us this summer from Caltech. William has been working this summer with Kyle, and today he'll tell us about their project together, the formation of black hole white dwarf X-ray binaries in globular clusters.
Yep. Thank you, Graham, for the introduction. Guess we'll get into it. So globular clusters, they are these really massive clusters of stars. So they get up to 10 to the 6 stars that are very dense. So reaching like central densities of even up to 10 to the 6 stars per parsec cubed. So as like a point of reference, the stellar densities in the galactic field are only around on the order of like 10 to the -1 stars per parsec cubed. Globular clusters are also very old, so like 9 to 14 gigayears. So that just tells us that we're working with very evolved populations of stars that would have undergone a lot of interesting dynamical encounters and formed interesting objects. So in the picture there is 47 Tuc, one of the most massive and dense globular clusters out of the roughly 150 globular clusters that we've observed in the Milky Way. And it's home to a variety of interesting objects. So the structure of a globular cluster is largely determined by the dynamical gravitational interactions between the objects within it. So we know globular clusters contain lots of stellar mass black holes just due to stellar evolution. As the globular cluster ages, these black holes remain as the highest mass objects within the globular cluster because the higher mass stars would have all died by the time that we're looking at these globular clusters. So what happens is that as these black holes undergo dynamic gravitational interactions with other stars, they'll tend to kick these lower mass stars towards the outer edges of the globular cluster, while the black holes themselves sink towards the center, forming a really dense stellar environment in the core of the globular cluster. And this process is known as mass segregation. Inside this dense stellar environment, it's basically very prone to events such as really strong gravitational interactions happening, or even collisions between black holes and other stars. So the particular systems that we're interested in are black hole white dwarf X-ray binaries. So this is motivated by many recent observations of the specific binary systems. And just, I guess the formation dynamics are not very well understood. So this project is essentially just motivated by these observations to try and explain how they form and really how many we should be expecting to see. So for example, here in the picture, we have a really strong galactic candidate for a black hole white dwarf X-ray binary called 47 Tuc X9. And it's one of the strongest candidates that we have for such a system. So the formation, the ways that these systems can form, I guess the main formation channel that we're looking at for this project are black hole giant collisions. So what happens in a collision like this is that since the outer layers of the giant star are so diffuse, they're really loosely bound to the core of the giant. So when a black hole collides with a giant, the outer layers, they'll form a common envelope that gets quickly ejected on the timescale of a few days, resulting in a black hole giant core binary system, which as the system inspirals and ages, this core will then evolve into a white dwarf and then inspiraling into the black hole to form the X-ray binary that we're interested in. And this inspiral process is just due to gravitational wave emission. So in this project, we essentially modeled all of the key evolutionary phases of the formation of such a system. So we first used n-body simulations of globular clusters to identify the rates of these collisions. And then we looked at hydrodynamic simulations of the actual collisions themselves so that we can get an idea of the immediate post-collision properties of these binary systems. And then we modeled the binary evolution itself. So it's the gravitational wave inspiral stages and also the mass transfer and accretion stage to produce predictions for both the electromagnetic luminosity of these X-ray binaries and also the gravitational wave signal of these X-ray binaries. So the n-body simulations we used were use the cluster Monte Carlo code, so on the CMC code. And what these simulations did was that they modeled the orbits of the individual systems inside the globular cluster, so we can get an idea of the overall cluster evolution. They also modeled individual stars so that we can actually get these giants and black holes. And it also directly integrated strong gravitational encounters between between a few bodies. So for example, here we have the gravitational interactions between like 3 stars. And the simulations basically just integrated these really precisely and accurately, not only because like they're really important for the actual evolution of globular clusters themselves, but this is how we're able to even study like the formation of these binaries. So in this animation here, we can see that these few body encounters can lead to collisions between stellar objects. So it's resulting in a binary system. Yeah, so from these n-body simulations, we tracked around 300 of these collisions, and this produced a collision rate of around 1 collision per gigayear in each cluster. So in the plot here, I plotted giant mass versus black hole mass of each collision, and this just basically gives us an idea of like what we're working with. So from here, we essentially grabbed the median system as a representative system of all of our collisions. So what we then did was that we put this median system into a hydrodynamic simulation that uses the smooth particle hydrodynamics code Star Smasher that was performed by a colleague of my mentor, so James Lombardi. And this basically just produced parameters for the binary system after the collision. So here we're tracking the giant mass, the semi-major axes of the orbit, and the eccentricity of the orbit. So yeah, so we can see that like after the collision, we're pretty much just left with the core, like the lone core of the giant itself at around 0.1 solar masses, and the semi-major axis drops to around on the order of like 1 to a few solar radii. We're also left with a very eccentric binary, but as it inspirals, this eccentricity will decrease just due to the nature of gravitational wave radiation. So we essentially then just put this the parameters of the parameters of the resulting binary system into the binary evolution code Cosmic that models both the orbital properties of the binaries and also the mass transfer rate once the white dwarf inspirals into a black hole. So Cosmic basically told us that the gravitational wave inspiral time was within 100 million years. So that tells us that black hole giant collisions are definitely a viable formation channel for the systems that we're interested in. So as the white dwarf continues to inspiral, it'll begin mass transfer into the black hole. And you can see that Cosmic keeps track of all the orbital properties here. So see that the the binary separation also increases as it begins mass transfer, just due to orbital dynamics. And the mass transfer that Cosmic produces, we then convert into a luminosity, from which we can set rough expected luminosity bounds on what we expect to observe in both the Milky Way and in extragalactic sources out to around 20 megaparsecs. And from these luminosity bounds, essentially just taking the upper right-hand side limits of each shaded region, we can obtain an estimated observable lifetime for these systems. So now that we have a collision rate and also observable lifetime for each system, multiplying them together produces predictions for how many of these systems we expect to observe currently. So we predicted around 6 observable galactic sources and 1 observable source in globular clusters out to 20 megaparsecs. And the nice thing about this is that these predicted rates do largely agree with the observed rates of candidate systems. So like I said before, we have 47 Tuff X9 as a very prominent candidate in the Milky Way. And we also have a few strong candidates in extragalactic globular clusters. Yeah, so finally, we also calculated the gravitational wave strain of our binary systems. So what I've plotted here is essentially the gravitational wave signal strength plotted against the frequency of the binary orbit. So the big black line here shown is the LISA, so the sensitivity limit for the future space-based gravitational wave observatory that will be launched in the 2030s. It's called LISA. And essentially anything above this black line is observable by LISA. So here I plotted a few tracks of the of binaries at varying distances. So notably, we can see that the strength of the gravitational wave signal depends on the binary frequency, the mass, and also the distance that they are from us. So within each track, I've shown the inspiral phase of the binary in blue and the mass transfer phase of the binary in red. So we can see that galactic sources are definitely potential LISA sources. they have relatively high signal to noise ratios of up to like 100 or even 1,000, depending on when we catch them. So basically, our X-ray binaries do serve as definitely like promising potential sources for LISA. Just as long as we catch them in the right phase, so around like 10 million years before or after the onset of mass transfer. So yeah, and also like what another thing that makes these X-ray binaries particularly interesting to study is the actual shape of their tracks. So like more traditional like gravitational wave sources, such as like binary black hole mergers, their tracks would only travel towards the right of this plot as they inspiral and their orbital frequency continues to increase as, before they collide. While here, our X-ray binaries, they'll first inspiral, and then as they begin mass transferring, their binary separation increases again, causing them to turn around in their tracks as their orbital frequency decreases. Yeah. So just to conclude, we know black holes are observed in globular clusters as luminous X-ray sources. We've shown that black hole giant collisions are a key formation channel for black hole white dwarf X-ray binaries. And we made both electromagnetic and gravitational wave predictions for how many we expect to observe and what their signals would look like. Yeah, and thank you for listening to my talk, and I'm happy to answer any questions.
Very nice job, William. Questions for William? Tony?
It's not a question, but it's a comment as to this expands and forwards. It's gonna go into stable first states, where instead of being at a constant luminosity, it's gonna have high states and low states probably, because there's gonna be a hot star that provide early condition. And so you might actually only be able to observe it part of the fraction of the time, but when it is observable, it might actually be brighter. It's an alpha state, so that might be an interesting direction.
Yeah, definitely. I think here for the way that we've modeled it, we've just treated it as like a circular orbit. And I think Cosmic is also relatively, it's a really fast tool, and but it might not be as might not consider as many factors. So that's something that we'll definitely look at. Yeah.
Like a time average one, but it might actually be.
Yeah, definitely.
Other questions for William? Mike?
Yes.
Great job. So you've got this very impressive stack of different models. You've got CMC, you've got Star Smasher, you've got Cosmic, and all of that gets fed forward to get to your final result. In your opinion, which stage in this modeling stack is the most uncertain, which contributes most to your final sort of implicit error bar in your prediction?
Yeah, so I would say it would probably just be Cosmic, because of how it's there are more accurate binary evolution tools out there. We just use Cosmic because it was relatively fast, and it also produces relatively accurate results. But yeah, we could use other more precise tools. And also, setting the luminosity bounds, they're also relatively rough estimates for what we expect to observe. But yeah, mainly just in this stage of modeling the actual luminosity too.
Any other questions for William?
Can we condition some of the properties of a globular cluster that can form these extra binaries?
I'm sorry, could you repeat?
Are there properties of globular clusters that are helping in forming these extra binaries? And thinking, are they more likely to form more massive, more compact clusters, something like that?
Yeah, definitely. Yeah, I remember definitely the more massive globular clusters and globular clusters that had smaller radii tended to generate more of these collisions. Yeah, I think those were the main two factors that led to that really affected how often these collisions form, just their size and their mass.
All right, let's thank William again.